do we have a point? Bless you. Do we have a slope? Let's go find that slope at that point. You know what I'm saying, people? Let's go find that dy dx at that point of 1, 2. I'll see you guys there. DM, are you keeping your slope right here? Because you could.
Yeah.
You know what I mean?
Yeah.
You could. How many people are like, unicircle, where's pi over 2? What's that sign there? 1, right? 0, 1. I know, right, Danny? Honestly, that's why you're going to do this, buddy. Leave it right there. Seriously. But if you did simplify it, did anyone get a slope of 3 halves? Okay. If we got a slope of 3 halves, what's the equation of that tangent line? Y minus 2 equals 3 over 2, x minus 1. If I'm Danny Main, I'm writing y minus 2 equals 1/2 sine of pi over 2 times root 9. Danny, there's no shame in that. Oh, and then I got to do times x minus 1. This is getting you the same points, D.
Okay.
You know it's not getting you points if we don't get 3 over 2 here.
Yeah.
You know? Okay, then it says use that equation to approximate when x is 0.8. Do you agree 1 is pretty close to 0.8? What are we going to do to get that approximation? Plug in 0.8. Where are we plugging that? Right in for x. So regardless if you went Danny's style or my style, what do we have to do to both sides? Yeah, just move that 2 over. Danny's is going to look like y equals 2 plus 1/2 sine of pi over 2 times a root 9 times 0.8 minus 1. Danny's done there. The rest of us might say 3 has 0.8 minus 1 plus a 2 at the end. That 2 can be in the beginning or the end. I don't care. But you guys, both of these are right. And they love asking this as a free response. So D, don't get greedy about that slope. Because who cares, right?
Yep.
Okay. Then you guys, it says, it is known that my second derivative is positive. This goes back to that chart that we did yesterday. Is the approximation going to be an over or an underestimate? So if my second derivative is positive, that means that my acceleration is increasing or my slope of my function is increasing. And you agree if my function is concave up, those slopes were negative, 0, then positive. Those slopes are increasing. That's what would make my second derivative positive. So you're exactly right. Those, even though this is a terrible graph, that looks like a bird's nest, Laura, my goodness. These are all going to be underneath that function. So I agree. All we'd have to say, the approximation at x equals 0.8 is an underestimate because f double prime of x is greater than 0. That's the only explanation you need. Danny Main chugging his milk. Blah. It's taken out of a refrigerator, placed in a pan of hot water to be warmed. What? We're making hot cocoa, okay? The increasing function m models the temperature of the milk. So m is just the temp. Okay. T is the number of minutes since the bottle was placed in the pan. Blah, blah, blah. dmdt would be talking about what? The rate that the temperature of that bottle of milk is changing. Okay. All right. And then it says at t equals 0, the temp is 5. Use the line tangent to the graph at m is 0 to approximate m of 2. You guys, right here, when it says use the tangent line when t is 0, that means right there, go find the tangent line right there. Let's not go look at this next part. Use it right here. What would we need? We need a point and a slope. When t is 0, do we know what my point would be? Nice, Liv. She's saying, well, they said at t equals 0, the temp was 5. So my point is 0, 5. How could I get my slope? Plug that in, she says. dm dt at 0, 5 is going to be 1/4, 40 minus, which one is m? Is m 0 or is m 5? Doesn't it say t is 0? Yep. So maybe when we see that, I'm going to put a little t there. And then, Riker, it says m models the temp of the milk. And then it says m is degrees Celsius. So that helps me give me a little context. Because kind of Ben Matney, you know, we were talking about those variables. Like sometimes it's hard to figure those out. We'll just really look for the context from that problem. Okay, so I'm going to go put in my 5, right? Danny Main's going to leave it right there. Danny Main does not know what 40 minus 5 divided by a fourth is, okay? Truly, who cares? Let's just leave it. Is everyone else doing 35 fourths? Yeah. Okay, but Danny's going to leave it, okay? All right, what's my slope? Oh, the equation of this line then, guys, they do get ornery about this. There's no y's and x's now. What are my variables? T's and m's, so we got to use the variables. That they do get ornery about that. So instead of y minus y, it needs to be an m minus an m. So we're going to say m minus, careful. Yes, it's okay. M minus 5, right? Equals, what was my slope? 35 fourths. Danny Main, don't you dare. You're going to write 1/4, 40 minus 5. And then instead of x minus 0, what are we going to say? T minus 0. Could we just say t? Sure. Great, you guys. It says use that tangent line. Done. We just got a point to approximate m of 2. Just right here, it says m of t. So that 2 is just my t value, which is really just my x value. So what's m going to equal? 35 fourths times 2 plus 5? Done. We're going to think this through then. Check this out. Write an expression for the second derivative. They gave us the first derivative. We got to go get the second derivative. What do you want to do to that maybe before we find the first derivative? Second derivative? Could I distribute that? Could I just say my dm dt is 10 minus 1/4 m? Is that right? Distributed that right? Now they want the second derivative. What's the derivative of 10? 0. Be careful, be careful. What is the derivative of negative 1/4 m with respect to time?
1/4 dm dt.
So good, buddy. Don't forget that negative. Negative 1/4 dm dt. Will Turner, so good. Don't forget, if you struggled with that, that's like, what's the derivative of negative 1/4 x? Oh, you're like, oh, negative 1/4. But then we do have to do the dm dt. Very good. Then it says, determine whether that approximation is an under or an overestimate when x was 2. When my x was 2. That's as far as I wanted to take it right now. I just want to make sure that we felt good taking that second derivative. I'm good with not plugging in anything for that next step. Here's what we got to do about L'Hopital's. You guys, we saw these back in August. And now there's a nice cheat sheet. Let me remind you what we had to do to these in August. We always plug in that 2 to start. What would we get if I plugged in that 2 up here? 4 plus is 6 minus 6. 0 over 0. And when that happened in the fall, we had to factor. And we had to say, oh my gosh, what is the top toot into, you guys? The top would toot into negative 2 and 3 multiplies to be negative 6, adds to be 1. Agreed? In the bottom? Difference of squares? X plus 2x minus 2. Does anything cancel? And we were left with the limit as x approaches 2 of x plus 3 over x plus 2. And when I plug that back in, what would I get then? 5 over 4. We could do this way. That's fine. But Mr. L'Hopital or Mr. Bernoulli, whoever we want to give credit to, came up with a faster way. And I couldn't teach it to you in the fall because we didn't know how to take a derivative. But Mr. L'Hopital says anytime you get 0 over 0 or infinity over infinity, but we'll do another one like that, then you can just use this shortcut. And the shortcut is just take the derivative of the top. What's the derivative of the top, you guys? 2x plus. Great. What's the derivative of the bottom? 2x. Evaluate that same limit that they had right there as x approaches 2. What happens when I plug that 2 in there? It becomes 5 over 4. Do we like L'Hopital's? Did he save us some time? Oh my gosh, is right. Why couldn't I teach that to you before? You didn't know the power rule before. You know what I'm saying? So, Mr. L'Hopital's, very convenient. Anytime we get 0 over 0 or infinity over infinity. Did we have to do quotient rule? Nope. Did we have to do product rule? Nope. It's just take the derivative of the top and take the derivative of the bottom every time. Not bad. So, right here, ooh, Danny Man, good luck with this unit circle. What if I plug that 0 in right away? What would I get here? 1 minus cosine at 0. 0 is here, very good. So we got 1 minus 1 on top over 0. Do you agree that's 0 over 0? So right away, that's like, okay, now I can use that L'Hopital's rule. That L'Hopital's rule just says take the derivative of the top. What's the derivative of the top? Sine of 2x times, good, there's that chain rule. Liv wasn't even here yesterday, and she's not skipped a beat. She says, okay, the derivative of negative cosine is positive sine. Leave my inner times the derivative of the inner. So good. What's the derivative of the bottom? 5. Now we go plug in that limit again. If I plug in a 0 there, sine at 0. 0, 2 times 0, over 5. No, 0 can be over 5. Yeah, it would just get a 0. And we can have a 0 over a number. That's okay to have my limit just be equal to 0. Okay. So the question is, you can only use L'Hopital's when my top over my bottom is 0 over 0 or infinity over infinity. So it says, should you apply L'Hopital's to these following situations? To the 4 following functions, I only gave you 3. What a goober. Here we go. What's the sign at 0? 0 over, wouldn't that be 0 over what? Negative 1. What does that equal? 0. So this one is no L'Hopital's. The limit here is actually just 0. We're done. You got a number, and that's all that we're really looking for with limits. So this one's not L'Hopital's. We would have just gotten it by substitution. How about this one? Sine of 0 is 0 over 0. This one would be, yes, I've got to do L'Hopital's. Let's do it. What's the derivative of the top? Cosine of x minus 2. We left the inner. What's the derivative of that inner? 1. So I'm good. I don't need to worry about that. Over derivative of the bottom. 2x. What happens when I go plug in my 2 now? Done. We love Lopi. We love Lopi. I call him Lopi, like we're pals. How about this guy? Anyone know what the ln of 1 is? We have to memorize this one. ln of 1 is 0. We got to have that one memorized. What would we get on the bottom? 0. Should we use L'Hopital's? You know it. What's the derivative of the top? 1 over x. Good job. I was worried that you guys were going to hesitate on that. Over derivative of the bottom. 2x. You guys, we're going to just plug in that 1. Final answer? We love Lopi. Okay. Table below gives some selected values. Find this limit. You guys, no matter what, if we're thinking L'Hopital's, no matter what, you always just plug in what you started with to see what we get. This would be f of what minus 1? 6 minus 1, so that's f of 5, right? Over 0. What the heck is f of 5? Do we know that from my chart? F of 5 is 0, right? F of 5 is 0. So do we use L'Hopital's on this? Yeah, we got a 0 over a 0. So L'Hopital's just says keep that limit, the limit as x approaches 3, and we got to do the derivative of the top. Ooh! What rule are we doing to take the derivative of this top? Chain rule. What's the derivative of that outer? Leave the inner.
When x is 5.
1 sec, buddy.
F of 5.
Give me 1 sec. Derivative of the outer, we left the inner times the derivative of the inner. Perfect. Over, what's the derivative of the bottom? Perfect. Okay, you guys. We took the derivative of the top. We took the derivative of the bottom. Now we plug that 3 in again. Psh, psh. The limit as x approaches 3 of f prime of 5 times 2 over 6. Do I want to do f prime of 10 or f prime of 5? F prime of 5, very good, you guys. Do we know what f prime of 5 is? F prime of 5 is 7. Anyone getting 7/3? Great. Okay, let's try this next one. So this looks like a blast. Agreed. Let's just always plug in that 0 first. If we get a number, then we're done. E to the 0. 1 minus cosine at 0. 1 minus 0 over. Yeah, you agree we're getting 0 over 0? We're using Lopi. Derivative of the top. Derivative of e to the x. E to the x. Derivative of negative cosine. Positive sine. Derivative of negative 2x. Minus 2. Over. Derivative of the bottom. Beautiful. Just go plug it in, y'all. E to the 0 again. 1 plus sine of 0. Say again. 0. Minus 2 over a negative 2. JC, what was your final answer? Love it. Oh, wait, wouldn't it be positive 1/2? Right, because they were both negative. Good call. Got me too, JC. The thing, though, is what happens if we start talking about infinities? What happens when I plug in an infinity here? What do you think infinity times infinity times infinity is going to get me? Infinity. Agreed. What do you think e to the infinity is going to be? Let me remind you what an e graph looks like. Here's what e looks like. As x goes to infinity, what do you think those y's are going to do? They're also going to go to infinity. So L'Hopital also works when we get infinity over infinity. L'Hopital is the exact same thing. So now let's go take the derivative of the top. I'm going to say, all right, the limit as x approaches infinity. What's the derivative of x cubed? Is 3x squared. What's the derivative of e to the 3x? E to the 3x times 3. So I'm going to write that as 3e to the 3x. You guys down with that? Could I cross out my 3's? Okay. What happens when I plug that infinity in? What's infinity times infinity? Infinity. And what about e to the 3 times infinity? It's still going to be infinity. And this is what L'Hopital's is GOAT for. He goes, oh, you got the same thing? Just do my rule again. He goes, don't you worry. Just do it again. If this was the function that we had before, he says just take the derivative of the top and the derivative of the bottom again. We're going to do it as many times as we need till we get an answer. What's up?
Is it 0?
Let's see. Let's go see. So the derivative of the top. What's the derivative of x squared? 2x. What's the derivative of the bottom? E to the 3x times 3. Do you agree my 2 and my 3 don't cancel out this time? That's okay. What's 2 times infinity? It's still infinity, right? What's 3 times e to the infinity? I'm still going when x is infinity. What's my y still doing? Still going to infinity. This is still infinity over infinity. And L'Hopital goes, don't you fret. Just do it again. Just do it again. You're on to something, Thomas. I think you got it. Just do it again. So this one says, all right, we're going to just do this again as many times until we don't get this indeterminate form. What's the derivative of the top? 2. I no longer have an x. That's good. What's the derivative of this bottom?
6.
Good. It's one of those two. 6 9 e to the 3x or, well, 6 e to the 3x or 9 e to the 3x.
Oh, yeah, it's 9.
It is 9. How'd you know that, buddy?
Because it's multiplication.
Yeah, he's saying, no, the derivative of e to the anything is just leave it times the derivative of that exponent, which was just an extra 3. So this was 2 over 9 e to the 3x. You guys, you plug that infinity in wherever there's an x. What's 2 divided infinitely many times? I've got $2 that I need to share with infinite amount of people. How much money are we getting? 0. Thomas, how'd you know that, dude?
Who's a guess?
Oh, love it. Okay, this is the stuff that's driven you crazy, people. This is that formal definition of the derivative. But guess what? We can just do Mr. L'Hopital. If h is 0, what would I have on the top? ln of 4 minus ln of 4 over. Okay. So if I get 0 over 0, you get to do Mr. L'Hopital. What is the derivative of the top? Be careful. Natural log is 1 over 4 plus h times the derivative of 4 plus h. Derivative of 4 is just 0. Derivative of h is just 1, so we don't have to worry about it. Minus, what's the derivative of ln of 4? 1/4 times the derivative of the 4. Yeah, so this is just a constant, actually. Ln of 4 is just a number, so the derivative of that is going to just be 0. All over the derivative of h. 1. Guys, go plug in that h is 0. How much do we love Mr. Lopi? Wouldn't that just be 1/4? Let's keep going. What do you think is going to happen if I plug in infinity, cube it, subtract some infinities, add some infinities, over some infinities, subtract it, add? What do you think we're going to get? Infinity over infinity. Agreed. Guys, don't overthink those. If we're plugging in infinities and cubing it, minus this guy, squared, you're like, well, would those cancel out? Infinities are ungraspable numbers. So we're going to have infinity over infinity. Let's take a derivative. Let's take a derivative. What's the derivative of x cubed? 3x squared minus 4x plus, beautiful. Derivative of the bottom, minus, perfect, plus, good. You guys, L'Hopital says, all right, just go plug that infinity back in. What are we going to get? Lots of infinities on the top and lots of them on the bottom, so much so that we just have an infinity over infinity again. And L'Hopital says, cool. Do it again. Do my rule again. Thomas, you think you got your answer?
Yeah.
I love it. What's the derivative of 3x squared? 6x minus 4 over 24x minus 6. We're getting there, people. We're getting there. But wouldn't I still have an infinity over an infinity? 6 infinities minus 4 is still going to give me an infinity on the top. 24 infinities minus 6 is still going to give me an infinity on the bottom. Don't love Lopi until we get a number. So we do it one more time. The limit as x approaches infinity. What's the derivative of 6x? Derivative of 24x. Can I even plug an infinity in there? No, 6/24 is the same as. Let's go to 1997. What happens if I plug a 1 in? Ooh. Do I want to do this one? I don't want to do this one. Here we go. Page 26. 2016, not that long ago. Multiple choice question. Let's plug in a 3. Tangent at 0. Tangent is sine over cosine. 0 over 1 is 0, so I'd get 0 over. If I plug in a 3 here, e to the 0 is 1 times 3. 3 minus 3. Are we at 0? Okay. As soon as you see that, you're like, bah, Mr. Lopi, let's do it. Limit as x approaches 3. Derivative of the top. Derivative of tangent. I really love seeing you guys think. Like, as soon as someone saw this, they were like this. I love seeing you guys think. Derivative of tangent is secant squared. Leave the angle. What's the derivative of that angle? Good. Over just the derivative of the bottom. The derivative of e, it always stays. We have 3e to the x minus 3 times the derivative of its exponent. What's the derivative of x minus 3? Say that again, right, Kurt? It's just 1. I'm not going to multiply that by 1, but it's just 1. Minus. Good, you guys. Whoo! Uh-oh, Danny's crying because we got to go unit circle. Secant at 0, then we want to square it. You guys, 0's here. Secant is the reciprocal of cosine. What is the cosine here? What's the reciprocal of 1? Then we have to square it. 1 over x is 3. I'd have e to the 0 is going to get me 1 times that 3. 3 minus 1. Whew. Okay, peeps. Ooh, I think this is terrible. Fun fact, ours only have 4 question answers now, which is kind of nice. But to me, this is like 5 questions in one. Blah. Which of the following pairs is the limit as x approaches infinity of f over g infinite? What? F over g. So on this first one, A, they're saying if I put x squared plus 2x over x squared plus ln of x, that's me putting f over g. And they want us to analyze the limit as x approaches infinity. If I want to analyze the limit as x approaches infinity, I took that from right here. If I plug in infinity here, what do we get? Infinity squared plus 2 infinities over infinity squared plus ln of as x goes to infinity, still going to be infinity. So maybe we start with that. Now let's do a L'Hopital. If we got infinity over infinity, let's do a L'Hopital to that guy. What would that get me then if I took the derivative of the top? 2x plus 2. What about the bottom? 2x plus 1 over x. What do you think that's going to get us if we plug in infinity? Infinity over, that would get me 2 infinities. What would this get me? 1 over infinity? That would get me a 0, right? But I still have infinity down here, but plus is 0. Just good to know. Okay. Whew. Got to do it again. How might I want to rewrite this so when I take that derivative that I don't do quotient rule? How could I rewrite that? That's the same as x to the negative 1. Okay, that's something to think about. Okay, so if I go to take the derivative of the top, what are we getting on the top? 2 over the bottom. 2, what would this derivative get me? Minus
Or negative, yeah.
x to the negative 2. To your point, Mr. Wills, is 2 over 2 minus 1 over x squared. Yeah? And Wills, they want when x is infinity. Can't plug it in up top. What would I get when I plug it on the bottom? 0 right here, right?
Oh, yeah, it shouldn't be 0.
So I'd have 2 on the top over 2 minus 0. What's that going to get me?
1.
Yeah. Wow, that was a lot of work. To Danny's point, he's like, I'm sorry, that was just question A, part A. Is that infinite? No, we got an actual number for it. It says which one of these functions, when I do f over g, would get me infinity. This one, after a couple L'Hopitals, got me 1. So A is out. Whew. Anyone have any ideas that we might want to try, now knowing what it goes into it, to see if we would maybe end up with an infinity? Or should we just go to B? Yes, sorry, Zaid.
I would just cross off B and C
Wait, how
because
does
I know
infinity
that
go to
like
0?
that one you
On B, what's f over g? What's 3x cubed over x to the 4th? When I plug in infinities there. Thanks, Iono. He says infinity over infinity. What's the derivative of the top now going to be? 9x squared over 4x cubed. Very good. And if we analyze that to infinity, would we still have infinity over an infinity? Yeah. Gotta do it again. Derivative of the top? 18x, derivative of the bottom. So good. We're still getting infinity over infinity? Will we get infinity over infinity forever? No, if I do that one more time, derivative of 18x.
We'll just cross that out now.
We can just cross that out. He's like, I know now, wouldn't we get 18 over 0? I'm sorry, 18 over infinity. 18 divided infinitely many times is going to get me 0. That's not infinity.
Is it going to be? It's the exponent at the top's got to be bigger than
The exponent on the top has to be bigger. I love that logic. The exponent on the top has to be bigger. And so you're seeing that. I got you. I don't know, but these are all a little uncomfortable, aren't they? These are all a little uncomfy. Let's see. I think I kind of want to go through each just real fast because I want to look at C. Because if I'm talking for C, the limit as x approaches infinity of 3 to the x over x cubed. What's going to be 3 to the x? Just a reminder again, like e to the x, 3 to the x looks like that. As x goes to infinity, what's this going to do? Infinity. Over infinity times infinity times infinity, infinity. Okay? This is a good reminder of what this derivative rule is of 3 to the x. The derivative of 3 to the x is still 3 to the x, ln of the base. The reason when we've had e, we haven't had to worry about that. If I said, hey, what's the derivative of e to the 3x? It's e to the 3x times, well, let me just say e to the x. The derivative of e to the x is just e to the x. Technically, it's times ln of e, which is just 1, so we haven't had to worry about it. It's always ln of that base, so we don't have to worry about it. But when that base is an e, we do have to worry about it. Whew, what's the derivative of that bottom going to get us? 3x squared. Okay, people. We're almost there. We're almost there. What's 3 to the x? 3 to the infinity, my bad. 3 to the infinity? Infinity. Over infinity. We got to do it again. Here's my question, people. Let's do this one more time. I think you're going to see the trend. What? Are we going to just keep multiplying this by ln of 3? The derivative of ln of 3, 3 to the x, is still ln of 3, 3 to the x, ln of 3. So again, anything with that x as the exponent, the derivative is what you started with times the ln of the base. What's the bottom going to turn into? 6x. Are we still infinity over infinity? This is the worst problem ever. Last one. Last time we got to do it, people. The derivative of the top now, just another ln of 3, right? So the derivative of the top is ln of 3, I'm going to just say squared, times 3x. 3 to the, yeah, now times an ln of 3. I agree, yep. All over 6. Now when I plug in that infinity, what am I going to get on top? Infinity over 6 is going to be infinity. Dude, that was gross.